For most of the 20th century, it was believed by geologists, paleontologists, archaeologists, and other scientists that the rates and magnitudes of global environmental change, such as we have experienced during the past couple of centuries since the dawn of the scientific revolution, were the norm throughout most of Earth history, especially during the time which we humans have existed. Researchers and others who questioned the strictly gradualistic models of change, who saw the effects of large-scale catastrophes and disruptions in the landscapes around them, were consigned to the fringe, considered crackpots or pseudoscientists at best. But this entrenched belief in gradualism began to unravel in the year 1980, when three teams of researchers all concluded, independently, that the extinction of the dinosaurs was the result of a great worldwide catastrophe induced by a cosmic impact. In the aftermath of that evolutionary development, it has become respectable to explore the possibility of cataclysmic change, not only affecting the planet as a whole, but the human species as well. As a result of this new insight, we are compelled now to ask, to what extent have global catastrophes affected the rise and fall of human civilization? Join me as we dive into this critically important question. Everyone, welcome to another episode of Squaring the Circle. I'm your host, Randall Carlson, and hopefully the rumor is that I am going to be joined by my friend and colleague, John Arthur. Well, sure enough, it wasn't a mere rumor. There he is, in real life.
The rumors of my appearance are not exaggerated. I will be here producing in the control room. Glad to be here.
It's so comforting to know, John, that you are there in the control room handling things.
Well, it's an honor to be here.
Preventing the very real possibility of catastrophe. We had a near catastrophe a little earlier when my microphone came unscrewed from the stand, and I'm glad it happened before we started recording instead of happening in the middle of the recording.
Well, so for those of you who wish to say this, you can no longer claim that Randall has a screw loose. They've all been tightened. So we're all good.
At least this one.
At least that one.
There actually may be a couple of screws that could just use a little more tightening. Maybe they're not loose in the sense that they're about to fall apart. Anyways, we are going to be talking about catastrophes, which is something that we seem to be inclined to do. And there's a reason for that. I think the reason is simply that we now know, since in the introductory remarks I mentioned the year 1980. Well, 1980 was, to me, was an inflection point. It was a turning point. Because if you go, even though, you can see the developments leading up to it. Yes, there were more and more scientists, like throughout the 70s, that were beginning to raise questions. But the dominant paradigm was still strictly uniformity, gradualism, and so on. But with the three publications in 1980, it really did open the door to realization that, wow, yeah, there have been great catastrophes, and it's likely that, something from space from time to time strikes the Earth with severe consequences. And in the aftermath of that, when we see throughout the 80s, we see that once scientists began to take a deeper look and consider that this was a very real possibility in Earth history, they started discovering more and more craters and impact structures, astrobleeds. My understanding of the difference, why we would use two different terms, one crater and astrobleed, is that a crater is going to be the classic bowl-shaped that we can actually see, the evidence that, a ringed structure, circular structure, it has some depth to it. And then, of course, the associated impact proxies that make the case that, yeah, it's not volcanic or not a salt dome. It's an impact of something from out there, right? Well, once we've been taking a look, of course, we started finding them more and more and more until now there's, oh gosh, at least 200. I think more than 200. Actually, I think it's quite a few more than 200, but there is a whole rigorous process of vetting, of confirming that some of these structures that are being found are in fact from hypervelocity impact. Now, an astrobleem tends to be, astrobleem, like astro meaning star, and bleem, it comes from this, is the root of the word, like for example, blemish. It means also wound. So astrobleem literally means star wound. Okay, so an astrobleem, I think if we were going to have some fine distinctions here between the definition of the term crater and astrobleem, is that a crater is pretty much visible on the macro scale. You can see it. There it is. An astrobleem doesn't necessarily have to be. An astrobleem, like the KT boundary, 66 million year old crater, is buried under like half a kilometer of limestone sediment. You can't really see it from the surface, except for the ring of cenotes, which it might be interesting to talk about. But otherwise, the ring of cenotes has been known for a long time, but without any awareness that that ring of those sinkholes in the Yucatan were somehow connected to this buried astrobleem that we couldn't see. But now we have models of the astrobleem as it is, and there's others. You know, we could say the Chesapeake Bay astrobleem, which is buried. It's under Chesapeake Bay. We can't see it, but with the technologies available to us, ground penetrating radar and such, we can actually discern the outlines of it. But it is an evolving area of scientific research, and the more we learn, I think the more relevant it becomes to understanding not only the past history of life on Earth, but the past history of human life specifically on Earth, and our attempts to establish civilization, to the rise and fall of human civilization, which we now know there are many examples of ancient civilizations that once reigned very impressively, and then they disappeared. Why did they disappear? Well, it was generally always considered that it was due to internal factors, with the exception of warfare. And if they couldn't attribute the decline of a culture to strictly internal things, essentially the priorities, I guess, of that particular society, then it could be warfare. And, you know, some of these sites, for example, Abu Huraira, there was found a cultural layer which seemed to define the termination of that urban complex. But one of the things associated with that cultural layer, with that horizon, was charcoal. So the assumption was, well, there was war, right? There was a battle. They got wiped out in the battle. We don't know who they fought, but it was a war. Well, with the work of Stephen Collins and others, what we've now found is that that charcoal layer is infused with microspherules and other impact proxies prolifically enough that it's almost certain that it was a cosmic impact, something along the lines of the 1908 Tunguska explosion, but maybe even more powerful than that terminated. And, you know, we now know that there was what's called the Bronze Age collapse. There were two episodes of collapse, widespread collapse, that seemed to have terminated the Bronze Age. And that is something we definitely should dive into in greater detail and depth. But first of all, I think we need to kind of define the stage, look at some of the props that are on the stage, kind of get a backdrop and a context for then understanding these events better. So, and there's two things that we can say that I think there's two areas of science which are now importantly needed to come together. And they're defined on the one hand by geologists, and this, of course, is an oversimplification, but for the most part, geologists are looking down, right? They're looking at the earth. They're looking at the rocks. They're looking at what's below their feet, right? Then you have astronomers. They're looking up and out, right? Now, in the last couple of decades, we have the emergence of a new scientific discipline called the planetary geologist. Well, a planetary geologist necessarily now has to look up and out because you're looking at other planets. But the astronomers have been looking out into our cosmic neighborhood and discovering, say since 1980, that our cosmic neighborhood is far more densely populated than anyone had ever even imagined a half a century ago or a couple of generations ago. Secondly, geologists are finding the ubiquitous presence of craters and astroblems all around the Earth. I'm going to pause for just a minute to talk about our partners over at SHPO, who may save you a significant amount of headache in your day-to-day business. We sell a variety of geometry tools and models, like our beautiful platonic solids here at Randall Carlson LLC. And when it comes to managing shipping, e-commerce, and returns, we've been using SHPO for over 4 years now, and we're very pleased with their service. SHPO's interface is intuitive, the primary order page is easy to navigate, and we have enjoyed stellar technical support. If SHPO can help you with your needs, please use the code below to partner with a great company while supporting our work here at Squaring the Circle. Thanks, and now back to the show. And what is now a couple of hundred is probably only 10%, 15%, right? And there's a couple of other interesting developments too. When you think that the vast majority of now identified impact sites, craters and astroblems, are on land, but land is, only a little bit more than a quarter of the surface of the Earth. So right there, it's fair to assume that if we include the total surface area of the planet, including the oceans, there has to be at least 3 times more of impact events, which brings us up to about 600 events or more, right? Now, the other thing is that we look at the surface of the moon, and what is the most prevalent feature you see on the surface of the moon? Craters. Millions of them. When you take in the smaller ones, less than a half a kilometer in diameter, say, on the near side, on the far side, there's actually several million of them. Now, if it was not for plate tectonics and weathering, the environmental changes, the vegetation canopy that's constantly doing enormous work to the crust of the Earth. If we took all away those factors, we have to presume the Earth would probably look something like the moon. And we don't know how many, you look at some of the deep ocean areas, the layers, the thickness of sediment can be hundreds to thousands of feet thick. How many craters are there buried under that sediment?
Well, to your point, Mercury looks a lot like the moon. A lot of
Yes.
our planets have a significant amount of impactor events that they've been through.
Yes, all of the solid surface planets, the silicate planets from Mars in, have cratering. Jupiter's moons have cratering. I mean, all of the satellites that we see in the solar system have cratering. Cratering seems to be, and craters are the evidence of impacts. So it seems like impacts have been fundamental at all stages of development of our solar system. Well, so once it was accepted that the dinosaur extinction, and that extinction, which is now called the Cretaceous Paleogene, used to be called the Cretaceous Tertiary, when that took place, and it was accepted that there was an impact because the evidence became overwhelming that there was a cosmic impact associated with that, then paleontologists and scientists began to look at some of the other great extinction episodes in Earth history, which included the Permian Triassic, which I think at this point is still considered to be the most severe mass extinction, because you've got the fossil record going up to what was it, around 245 million years ago. I got to get refreshed on my geological timetable. Look up Permian Triassic extinction, and let's get the date on that. That's considered to be the biggest, and some most severe. And some of the estimates are that more than 90%, maybe 95% of all species, terrestrial and marine, went extinct. In fact, life itself almost became extinct on Earth in the aftermath of the PT boundary event.
So that is estimated to have been 251 million years ago.
Okay, so that's, I was saying 240, 244. So in the ballpark. But now the dates are constantly being refined. But 251 million years ago, according to the geological timetable. And then you've got the terminal Ordovician, you've got the end Devonian extinction, you've got the Jurassic Triassic, and then you've got, of course, the late Cretaceous. And then you've got lesser extinctions, like the extinction of 13,000 years ago barely ranks within the great extinction episodes of Earth history. Because we're talking about, the extinction, which we've discussed already quite a bit. What we saw is that the extinction, and it would qualify as a mass extinction, but we're looking at, a selective extinction, the top of the food chain. We saw that 44 kilograms or 100 pounds in body weight, roughly 3/4 of all those megafaunal species in North and South America went extinct. About 35%, I think we saw in the Eurasian continent went extinct. And what was it, somewhere between 10 and 15%. There are different ways of counting species, right? Like, do we look at an Indian elephant and an African elephant and call that two different species or one species of Proboscidea? There's kind of some judgment calls in there. So depending on whose data you use to get the total number of species. Now, but that's accepted. Now, there's discussion and arguments about the causes of these mass extinctions in Earth history. I think that, and I'm not alone in this, some of the other researchers that have spent many years looking at these, is that the extinction events are the result of what we might think of as perfect storms. Because there may be a set of integrated factors all affecting the stability of the biosphere. One, of course, the direct result of cosmic hypervelocity impacts. Another could very well be variability in the sun, because I think there's enough evidence now to suggest that from time to time there could be hyperactive solar events. That's something that needs to be explored. And since I've learned about the Kreutz sun grazers and the consequences of hypervelocity impacts into the solar chromosphere, it's starting to look like there is some kind of quantum response in the sun to these impacts. For one thing, because of the strong gravity field, the sun is the final destiny of most cosmic material that comes into the inner solar system. If it's not swept up by the planets, or impact planets, or swept up like in the Earth, we could be talking not only about impacts of macro scale objects, but we could also be talking about the accretion of cosmic dust. And cosmic dust is going to be the final end product of this hierarchical process of disintegration that starts like with, they say, a single comet nucleus, breaks into multiple nuclei, subnuclei, through a cascading series of disaggregations, if you want to call it that, with the end result being dust. Now, what happens if a planet like the Earth with an atmosphere passes through a stream of that cosmic dust? dust. Well, it actually looks like that happened between 536 and 540 AD, which is going to be one of the episodes of global change that we're going to really focus in on and unpack that, because it's happened relatively recently, and there's a whole body of mythology that has emerged around that period of time. And unpacking that's going to be extremely interesting because there's new work, and we'll soon be interviewing Dr. Dallas Abbott, and she has done some really exceptional work on that particular period. In fact, I just read her paper on the 540 AD event for the second time last weekend, just in preparation for having an intelligible interview with her. But anyways, the question now is, how many of those other... Oh, the third factor I failed to mention, besides hypervelocity impacts and extreme solar variability, is volcanism. Now, volcanism is interesting because we could think of it as an isolated phenomena, but I'm beginning more and more to believe that it's not. Because we actually see that in some of the great mass extinction episodes, tantalizing evidence, not convincing, not proof, but definitely enough evidence to consider it realistically as a factor, the evidence of cosmic impact. But simultaneous with that, huge volcanic events, particularly the magmatic events where you have enormous extrusion of magma. Like, for example, the delta traps in India looked like they were happening concurrently or subsequently to the Great Cretaceous Tertiary impact. Likewise, the Siberian traps up in Siberia, a vast extent of basaltic bedrock, there's actually a plume under that as well. And that looks like it dates right to the Permian Triassic. Taking a little bit of a detour here to tell a story that I think is going to be valuable. I was coming down the stairs, and I think somebody just ahead of me had spilled a little bit. My foot hit it, slid out from under me, and I tumbled down 3 or 4 stairs to the bottom. I sure banged up my left knee. It was painful, but I was very relieved to remember that I happened to pack my CBD from the gods salve. And I was really grateful that I had remembered to do that. So that night I put some of the salve on, went to bed. Though I've being in the construction and building industry, I've had many falls and injuries and stuff, and I figured I'm going to be laid up with this for a month. We drove home. I think it was 3 to 4 days later. I continued applying the salve, and I would say within a week I was getting around pretty good. I always bring the oil when I travel, and I'm now, after this episode, I'm like, okay, I'm always going to have the salve with me too. So a lot of schools of thought, yes, Permian Trias, the PT boundary. So a lot of schools of thought attribute the mass extinction of the various species 251 million years ago to this eruption of this tremendous magma volcanic eruption and the formation of this magma province, right? Now, was there an impact? I think there probably was. Again, the evidence is not conclusive, but it certainly is very suggestive that there was an impact as well. So there's a number of researchers, I think Michael Rampino is one, particularly who I've read recently, who really is now thinking that a lot of the mass extinctions are the result of this perfect storm of events. Now, it certainly is plausible that an hypervelocity impact, one of the effects of that, could be extreme volcanism, magma extrusion. That's not so exotic. Likewise, we also have seen evidence now, and we could maybe pull it up here before this episode is over. We've got now 2 instances where satellites have filmed hypervelocity impacts into the sun. And because of the sun's extreme mass, the gravity attraction of the sun accelerates an incoming comet nucleus to extreme velocities. Now, the faster it's moving when it plunges into the sun, the more kinetic energy is going to be released. And if the sun happens to be a quasi-stable star, maybe there's some mechanism within the star that can amplify the effects of a hypervelocity impact. I don't know if are you pulling up, looking for those videos?
So this is the video that you were asking for.
Mm-hmm.
Let's see, make sure we have that off, where you can see this impactor landing into the sun. And for those of you on audio, it's really quite interesting because you see this flare that occurs. Did you catch that?
Yeah.
See that plume right there?
Yep.
Yeah. And so that can lead to a coronal mass ejection. I mean, obviously, it makes perfect sense.
Yeah.
So what does that end up being like for the climate here on Earth?
Well, there we go. See,
worth studying.
Let's see. Let's play it. You're going to see the comet coming in from down here, roughly about 4 o'clock, coming in towards the sun. And then it encounters the sun. It's swallowed up by the sun, and then you'll see the consequence of it. Here we go. Let's get this out of the way. Here we go. Watch. Let's watch that again. You'll see the comet coming in. Boom!
Again, for those of you on audio, small comet going in, big coronal mass ejection going out. It's like a hollow point with a watermelon.
On the opposite side of the sun.
On the opposite side.
Yeah. Here it comes.
So what happens when the Earth's hit with all of that radiation?
Right. Well, we're going to be discussing that because there's a lot of new evidence accruing showing. Here we go. Watch this one now. This is this. You can see the comet zooming in and boom. So if this turns out to be not just an anomaly, which is starting to look more and more like it's not, what we're looking at and have to start thinking about is an integrated system that the cosmos, the planets, they all interact. There's a whole set of feedback processes going on amongst the whole solar system, which we now know includes the Kuiper disk, the Oort cloud, that whole outer structure that it extends almost 2 light years out, almost halfway to the nearest star, in fact. And if we see that the influx of comets to the inner solar system that get swept into the sun, and that comet that we saw there was not an especially large one. I think it was, I think what I read was it is estimated to be about a Halley-sized comet, which would be 8 or 10 miles in diameter. But what would happen, like in the catastrophist models that are now conjecturing, quite legitimately, I would say, that somewhere between 25 and 30,000 years ago, possibly within that range, a very large comet nucleus came into the inner solar system and began to undergo a hierarchy of disintegrations, of which the Torrid family of meteor streams is the remnant of that large comet, which included, now we see it within this orbital system. We find Comet Rudnicki, Comet Encke, Oljato, an asteroid, the Torrid meteors, streams, also probably the Tunguska event of 1908. And why? Well, because Earth crosses the Torrid stream twice each year. Late June, early July, late October, early November. And I'm going to pull up a graphic here in a minute that we can look at to help get the picture. This diagram here shows the orbits of Torrid meteors. Now, this is going back to the work of Fred Whipple. Let's see, I think I got him. Oh, let's see. There he is. Oh, no, that's Clube. Fred Whipple, back in the 30s and 40s, he was one of the first astronomers who really studied comets and meteors and things like that. And he did a program where he began to photograph Torrid meteors. And I think he got over 40 photographs of Torrid meteors. And he did like a time succession so that he was able to capture enough of the elliptical orbit of these meteors and the timing that he was able to recreate the elliptical orbit of the whole meteor. Now, these meteors, there's some deviation within the orbit, but what he did here is what I did was I went to his data of the 40 or 45 meteor photographs, whatever it was that he did, and I took the two extremes of orbits, and that's what's you see here in orange. So you follow one of these around like this. This one, it's aphelion, which is its furthest distance from the sun, is less, say, than this one. This is number 712, and this is number 697. So they were all labeled with numbers. So these two orbits, I chose those two because they more or less define the outer boundaries of the stream. Okay, now we go back to here, and we have right here, if you can see, this is the orbit of Mars, this outer white circle, and then we have the orbit of Earth, and we have the orbit of Venus, and then we have the orbit of Mercury. But we're interested in the orbit of the Earth, and all of these are going, from our vantage point here, counterclockwise, right? As is the orbital motion of the Torrid meteor stream. So if I go to this, I've kind of done a little infill here, and I provided some dates. So again, Earth is moving around here, and then it crosses the stream, and this is the summertime Torrids, around June, like it says here, around June 30th. It takes about 10 days, 12 days for the Earth to entirely cross the stream. The Torrid stream is one of the more diffuse streams, and which suggests it's probably older because there's been more time for the material to disperse throughout the orbit. Right? A younger stream like the Geminids, for example, I think the Earth crosses the stream in a couple of days. Right? So now you see late June, early July, it's crossing the stream. It comes on around like this. Then late October, early November, it crosses the stream again. Because the Torrid stream lays very close to the plane of the ecliptic, which is the orbital plane of the planets. To be more precise, it's the orbital plane of the Earth itself, but all the other planets lie more or less fairly close to that plane. So we can kind of refer to the plane of the ecliptic as being the orbital plane of the planets. Now, when it's in summer, notice here, Earth is crossing, but notice that the stream has just only recently made its perihelion passage, meaning its closest passage to the sun. So if we're crossing the stream and you're looking at an object, a Torrid meteor, or a fireball or an asteroid coming through here, well, you see right here, you have to look up into the direction of the sun. So the sun is going to blind you. It's going to blot it out. You're not going to see it's not good. And that's what happened that June 30th morning in 1908, is that the Tunguska object came in from a region of space almost directly bullseyed on the sun. In fact, when you read through the eyewitness accounts, people say like it looked like the sun split in two. The object was born out of the sun. It disgorged from the sun, etc. Right? Now, when you come to the fall time Torrids, to look upstream, you're looking out into space. You're looking away from the sun. You see that difference? So obviously, a Torrid meteor or a fireball, whatever it might be, is going to be a lot more visible in the fall than it is in the summer. That's important. Now, when you're looking upstream, here's the line of sight. If you're here, the Earth is crossing the stream, the line of sight leads out into space, and it almost bullseyes on the Pleiades. And the Pleiades, in classical depictions, is the shoulder of the bull Taurus, and hence the name of the Torrid meteor shower, from Taurus the bull, right? Now, this is not something we're going to get into today and here, but there's some extremely interesting symbolism associated with the Pleiades and the bull symbolism and so on that suggests that there was a tradition. In fact, in some cases, like there's an old Jewish legend that when God decided to destroy the earth with a great flood, he pulled one of the stars out of the Pleiades and threw it at the earth. That's an actual legend. It's an old Jewish legend. And there's more. But we'll not get into that territory today, but it's very potent, interesting stuff, because it really does imply that our ancestors had a much more sophisticated understanding about these kind of cosmological phenomena than they've been given credit for. Particularly when we look at Mithraism, one of the great competitive religions to Christianity in the early centuries AD, had very interesting symbolism about the bull. And Mithras is depicted as stabbing a sword into the shoulder of the bull. And if you look at the classical depictions of the bull and the Pleiades is prominently the bull's shoulder. And then, of course, what you see in the Mithraic depictions is that Mithras is stabbing the sword into the bull's shoulder, into the Pleiades, and you see this outpouring that presumably you would think, a sword into the bull, he's bleeding, and this copious blood is coming forth. However, there may be an alternate meaning as well, because what's likely is that if there were extreme multi-impact events in the past, when the Torrid stream, and there is evidence that the Torrid stream was much more active in the past, that people all over the world from time to time witnessed things that left an indelible impression on their consciousness, and perhaps even triggered catastrophes. And, as you're going to find out, as we unpack what we now know about hypervelocity impacts in general, and the Younger Dryas impact hypothesis specifically, is that there is evidence for the objects that struck the Earth during the Younger Dryas were Torrid related. In fact, after we did our podcast on Joe Rogan, we got a letter from, which I'll read at some point. I don't have it in front of me now, but I can pull it up. But we got a letter sort of congratulating from William Napier, who has been part of this team in England that has been exploring what's called coherent catastrophism, which is the leading into this idea of coherent catastrophism is a great term for what we were just talking about, this integrated model of impacts, volcanism, solar outbursts, and so forth. These guys have been doing since the 1980s. I have a book right up on my shelf there called The Cosmic Serpent, published in 1980, where they're beginning to propose these ideas that there's this integrated model of catastrophism. Anyways, we got a very nice complimentary letter from Bill Napier talking about pretty much what we were just talking about here. So this is the Torrid meteor sheet. If you look down here at the bottom, you see orbits of 2 Torrid meteors. Number 697, which was photographed on October 31st, 1937, and number 712, which was photographed on November 10th, 1937. And so this defines the two, and pretty much also sets the boundaries or the limits of the stream itself. So outside those lines, you're not going to find much activity. And that's the importance of this. So it's very interesting stuff. And anyhow, so we're in a position now where we're recognizing that many of the great extinctions in Earth history were probably triggered by cosmic impact, and then could have had secondary consequences in terms of, it's far more likely that impacts are going to trigger volcanism than the other way around. And then if you have a large comet breaking up in the inner solar system, you might have multiple repeated incursions of comets into the chromosphere of the sun. What would happen if we had a succession of very closely spaced impacts into the sun? Is it possible then that there could be a reciprocal response or feedbacks introduced into the stability of the sun that could amplify the solar storms? I don't know. We're only at the very beginnings of understanding the role of the sun. But we are, 23, 24, 25 years now into, since the inception of the deployment of solar observing satellites. And so we're collecting a lot of new data, and it's coming in all the time. I don't have time to explore all of it. I wish I did. I need to be 3 or 4 people, because then I might be able to research all of the things that are interest me. But, hopefully as we pursue this, we're actually getting a lot of interest from really smart young people who are looking to make a serious exploration into this kind of knowledge. And one of the things I would like to see in the very near future is a whole school, an academic school, looking at the role of great catastrophes. Catastrophism 101. That's kind of what we're trying to do here. And over at our sister podcast that I do with Beckett Fusick, we've been looking at a lot of the flood evidence, but we haven't really tied that specifically to impacts yet. Although I think ultimately that's going to be exactly where this leads us, because it's looking more and more feasible that some kind of an impact event or series of impact events were associated with the great flood legends, even the biblical story of Noah, which I think would be a very interesting thing for us to unpack at some point, because of a possible impact into the Indian Ocean. And that's something that I'm definitely going to be talking to Dr. Abbott about, because she's done the work, probably the leading researcher of the evidence of tsunamis along the coastlines of the world. And some of these tsunamis are pretty mind-blowing. The one that struck the southern coast of Madagascar had to be at least 600 feet high when it made landfall. And I've explained that over on the big picture on the last episode.
You and I've talked about it too.
We have, yeah.
You have those 600-foot high chevrons deposited on.
Yes, that's what we're talking about. Exactly.
So it had to be at least. However, it could have been more.
We can actually determine what it is, how we know it was that, because we can see the chevrons making landfall, and then there's a 500-foot escarpment, right? We see the chevrons and the deposits of the run-in maybe something like 25 kilometers, something like that inland. But then we see the deposits on top of the escarpment as well. So I think it's at the base, I think it's maybe like 100 feet above sea level. And then it's another 500 feet to the top of the cliff. The wave overtopped, washed over the top of the cliff. So it had to be high enough to overwash the cliff, which puts it at least 600 feet high. Now, that, in my mind, satisfies the definition of a cataclysm. In fact, the word cataclysm comes from cataclysmos, which was the Greek term for their story of the Great Deluge. Because, you know, in the Greek mythology, you have Deucalion and Pyrrha, his wife. Unlike the biblical, we never know the name of Noah's wife in the biblical account, but we learn the name of Deucalion's wife. And the parallels are striking. He was given forewarning by Zeus in that particular tale that there was this great flood coming, and he built an ark, and that's how he survived. And then in the aftermath, there was also I think it names that he had his whole family with him in the ark. And then another variant of it is the Sumerian tale of Utnapishtim, who was the pilot of an ark, and he was forewarned by the god Ea. I don't remember if it was Ea or Enki. I think it was Ea. But he is in the descriptions of that flood account, he was joined by his family and the crew, and they survived this great flood, world-destroying flood in this ark that they built. So, I mean, there's many and then we find American legends talking about Native Americans surviving in the Great Canoe. This is wild stuff. Further, definitely worth looking into more, because I operate from the assumption that there's a lot more of scientific value in those ancient tales and legends and myths and folklore and so on than they've been given credit for. Now, they've been recognized as being valuable going back to the days of Carl Jung and his analysis of the archetypes of our subconscious. But to me, it's no surprise that the archetypes of these great events have somehow been encoded. They're so powerful that they would become encoded in our consciousness and passed down through generation after generation. Anyways, back to impacts. Let me read a quote from Bill Napier and Victor Klube that was published in 1990 in a book called The Cosmic Winter, which, of course, could be a good lead-in to the Younger Dryas, because that's what we're talking about, a cosmic winter. Now, they aren't making this quote is not any specific relevance to the Younger Dryas. But, so here we go. 1990, the cosmic winter. So the long evolution of the Earth, then, is distinguished by a relatively steady evolution superimposed on which are rapid, sometimes overwhelming changes, whether in the evolution of life or mountain building or even disturbances in the core itself. Many geologists over the years have voiced the suspicion that these changes have a galactic periodicity, and have speculated that somehow the galaxy is affecting the affairs of Earth. What was lacking in all these speculations was a mechanism for inducing the galactic periodicities, and it was not until the late 1970s, with the discovery of the molecular cloud and Apollo asteroid systems, that the mechanism was discovered. There are two main causative links in the chain connecting the galaxy and the Earth. The first of these is the ebb and flow of the galactic tide, which we have seen is reflected in the ebb and flow of comets into the interplanetary system. The second link is the existence of giant comets. Rare though they are, it is the giant comets which contain the bulk of the mass which enters the planetary system and it is their disintegration products which interact most strongly and directly with the Earth. As we have seen, the breakup of a very large comet will produce a wide range of debris, from objects 10 kilometers across to probably hundreds of kilometer-sized bodies, to temporary swarms of sub-kilometer objects, down to dust, in quantities sufficient to block the path of sunlight. We now ask, how would the Earth machine respond to the influx of such material? So this kind of gives, I think, a good summation of what we've just been talking about here. And this idea of coherent catastrophism actually encompassing phenomena on the galactic level, but then filtering all the way down to our realm here on the surface of this planet. So we're truly talking about expanding the purview of our own domain to a cosmic level. And I think that's got to be the next step. I think that the divine plan for humans on Earth involves us becoming much more aware of the great celestial realm, the heavens. We'll read this, and then we'll come back to the Clovis. Between 3 and 15th of November each year, the Earth runs through a meteor stream coming from a small area in the constellation of Taurus the Bull. A young stream made up of meteors not long released from their parent comet would be narrow and probably strong, and the Earth would pass through it in a half a day or so. The Geminid meteor stream is one such, the Earth encountering it on the 10th of December each year, and the shower being over by the 12th of December. The Torrid meteor stream, on the other hand, takes the Earth 12 days to cross, and it is not very intense. It looks old. It has two main branches, northern and southern, emerging from slightly different parts of the constellation, the branches being about equal intensity. Orbiting the Torrid meteor stream is a small comet, discovered in 1818 by Pons. An orbit was calculated for this comet by Johann Encke, a pupil of the famous mathematician Gauss, who had developed a method for calculating the orbits of bodies from their movement across the sky. There are about 100 known short-period comets. All of these, with the sole exception of Encke's comet, are in orbits which sooner or later lead to a close encounter with Jupiter and ejection from the solar system by the powerful gravitational pull of the planet. But Encke's comet has somehow established itself in a stable orbit, such that it never comes within the Jovian sphere of influence. It does, however, come close to Earth. In addition, and here's the critical part, in addition, there may be 1,000 or 2,000 asteroids over a kilometer across in orbits which make them a potential collision hazard with the Earth. None is more than about 10 kilometers across. Their surface is extremely dark, and fewer than 50 have been discovered. They are known as Apollo asteroids after the prototype discovered in 1932. Encke's comet is in fact the sole example of an active comet in an Apollo orbit. The orbit is highly elongated, and the comet may approach to within 0.34 astronomical units of the sun. An astronomical unit is the distance from the sun to the Earth. So 0.34, it's going to be right about a third of that distance between the sun and the Earth. And go out to about 4.1 astronomical units. The comet's orbit is inclined at only 12 degrees to that of the Earth's. This low inclination and the shortness of the orbital period ensure that there is frequent interaction between the Earth and the material of the Torrid stream, with the potential for occasional very close encounters with Encke's comet, or the rest of the material in that stream. And that brings us back again to the discussion we just had in showing that that the Tunguska object is not proven it was part of it, but the time of year was ideal, and the position in the sky from which it emerged was ideal. Both of those would be consistent with the Torrid object of 1908 being a part of the Torrid stream. And then this quote, I think, really kind of nails it. Peter Tyson, 1995, Comet Busters, Technology Review. Recent studies have shown that a host of fair-sized pieces could have more devastating global consequences than a single winter-causing object by igniting many separate conflagrations that merge into a global firestorm. And I think this is more the model we have to look at when talking about the Younger Dryas impact. And a lot of the critics have invoked this oversimplified model that one object randomly coming from space with no particular orbital structure or pattern to it hits the Earth, and then have shown what they do is they create this straw man model and show that it couldn't work to accomplish what the proponents of the Younger Dryas impact hypothesis are saying. And they're right. But their model is not the model. I think at this point that idea has been discredited for probably at least a decade now.
It's your neighbors who do the worst to you, as opposed to those who come from out of town. It's the neighboring asteroids and comets that we got to be worried about. That's what I'm hearing.
Well, along those lines, I wonder if we should actually address this from 1913, an extraordinary meteoric display. Published in the Journal of the British Astronomical Association from 1913. Now, for all the listeners, where else are you going to get this kind of information brought right to your computer screen? I've done a lot of work, invested a lot of time in bringing this information together. So I hope people appreciate that. Okay, so at about 9:05 p.m., 9:30 p.m. on the 9th of February, 1913, there suddenly appeared in the northwestern sky a fiery red body, which quickly grew larger as it came nearer, and which was then seen to be followed by a long tail. To some observers, the tail seemed like the glare from the open door of a furnace. To others, it was like the illumination from a searchlight. To others, like the stream of sparks blown away from a burning chimney by a strong wind. The body moved on a perfectly horizontal path with peculiar, majestic, dignified deliberation, and continuing its course, it moved on to the southeast, where it disappeared in the distance. Before the astonishment aroused by this first meteor had subsided, other bodies were seen coming from the northwest, emerging from precisely the same place as the first one. Onward they moved, at the same deliberate pace in twos and threes, with tails streaming behind. They all traversed the same path and headed for the same point in the southeast. Gradually, the bodies became smaller until the last ones were but red sparks, some of which were snuffed out before they reached their destination. As to the number of bodies, there was a great diversity of statement. The usual estimate was from 15 to 20. Some said 60 to 100, while others said there were thousands. The entire time occupied by the display was about 3 minutes. Just as the bodies were vanishing, there was heard in many places a rumbling sound like distant thunder. The stretch of country over which the display was seen is unprecedented. In the present case, persons dwelling 2,500 miles apart saw the same bodies. Moreover, the descriptions furnished by observers in Bermuda, in Ontario, and in Saskatchewan do not materially differ. Observations of the size of the bodies were very discordant, but there is sufficient evidence to show that they were of considerable size. Several observers considered the leading body to have a diameter equal to that of the full moon, or nearly so. One observer estimated the diameter at half that of the full moon, and another at 1/15 of the moon's diameter. The last estimate gives a real diameter of 123 feet. The largest bodies were probably at least 100 feet in diameter. The tail of the largest meteor is estimated to have been 39 miles long. Now let's bear in mind, when you're talking about 123 feet, we're getting right up into the realm of Tunguska. So this was a painting by Gustav Hahn of the Great Meteor Procession of 1913. And this shows the path from where it was first observers first saw it in Saskatchewan, coming down here and then passing out into the Atlantic Ocean. Now, if we look here, notice the path. It's crossing right over Lake Superior. It crosses over the northern end of Lake Michigan, Lake Huron, comes down here, passes between just to the south of Lake Ontario, passing over New York. Let's see, I believe it comes right roughly over Philadelphia, Montreal. A lot of cities lie along this path. So let's go back to this. If there were hundreds of bodies, let's go back to here. 15 to 20, some said 16 to 100, 60 to 100, while others said there were thousands. Let's just take some of the mean in here. 20, let's just take 20. Okay, the largest bodies were at least 100 feet in diameter. So within that procession, it's likely you had multiple, maybe even dozens, of Tunguska-sized objects. Now, 2,500 miles, they're passing essentially right parallel to the surface of the Earth. Most likely, they then passed out into space at some point, unless they fell into the Atlantic Ocean somewhere. But we don't know the ultimate fate of those objects. However, it's almost like they were captured into a temporary Earth orbit, followed more or less parallel to the surface of the Earth, and then probably almost like a stone skipping off the pond. If that angle had been just a little bit more oblique, can you imagine?
Well, even the Atlantic hypothesis, I mean,
Yeah.
that would have likely caused tsunami-sized waves.
Yes.
Multiple air bursts in the 15 megaton category would be pretty noticeable.
Now, so really what this is looking like is we came within a hair's breadth of a multiple impact event. 10, 12, 15, 20 possible or more Tunguska-like objects. Can you imagine?
And this was October, November?
February of 1913.
February
of 1913.
So 5 years after Tunguska.
February, though, so it's not the right time of year for
the Torrid.
Torrid.
It's something else entirely.
Something else entirely, yes. But this is important because it shows us that we were given a warning, in a sense. Look, 1908, here's one object. Boom. 15 megaton hydrogen bomb equivalent. Then what'd you say, 1930? 5 years later, here we're given this incredible display of a train of objects, maybe dozens of Tunguska-sized objects, just barely missing us. Can you imagine if those had impacted coming down over Ontario, over New England?
We'd be a lot less worried about cow farts and a lot more worried about a real actor of climate change.
Absolutely. Absolutely, we would have. But see, People don't know about this. This is not taught as part of our history. Now, I mean, there are probably astronomers and some fringe researchers that know about this event. But overall, I'm hoping as a result of this now, we increase the number of people who know about this event by at least a few 100,000, right? Which may be the total number of people, equivalent to the total number of people around the entire globe that presently know about it, right? One of the things, though, I fantasize about, how mind-blowing would it be to witness something like that? I mean, what astonishment, that was the word that was used, what astonishment it must have incited in the minds of people who witnessed this. Now, we've been talking about the Clovis. So this is from our friend, Dr. Malcolm LeCompte, who I was able to hang out with at the Cosmic Summit, and he has graciously agreed to be a guest on Squaring the Circle podcast. And we'll get to talk to him about his most recent research. But this goes back to a paper that he co-authored in 2012 that was published in the Proceedings of the National Academy of Sciences. Yeah, so this is from the abstract to this paper. Firestone et al., which just means and others, sampled sedimentary sequences at many sites across North America, Europe, and Asia. In sediments dated to the Younger Dryas onset or boundary, the YDB, approximately 12,900 calendar years ago, Firestone et al. Reported discovery of markers including nanodiamonds, aciniform soot, high-temperature melt glass, and magnetic microspherules attributed to cosmic impacts/airbursts. The microspherules were explained as either cosmic material ablation or terrestrial ejecta from a hypothesized North American impact. A number of independent groups have confirmed the presence of YDB spherules, but two have not. One of them, Suravel in 2009, collected and analyzed samples from 7 YDB sites, purportedly using the same protocol as Firestone et al., but did not find a single spherule in YDB sediments at 2 previously reported sites. To examine this discrepancy, we conducted an independent blind investigation at 2 sites common to both studies and a 3rd site investigated only by Suravel. Now, Suravel is part of the team that has been highly critical of the impact hypothesis. In any case, independently, Malcolm and his team did find abundant YDB microspherules at all 3 widely separated sites, consistent with the results of Firestone et al., and conclude that the analytical protocol employed by Suravel et al. Deviated significantly from that of Firestone. We're going to look at that. That's another thing we're going to look at as we unpack the pros and cons of the controversy surrounding Younger Dryas impact, right? Because the critics have raised some very valid points, legitimate points. But in the end, I think their attempts to dismiss this have failed. But it's helped hone some of the ideas because that's the way science works and is supposed to work. So then they go on here. Now, this is the Topper Quarry near Allendale, South Carolina. This was where we visited with by Dr. Al Goodyear, who's the lead archaeologist on the site. I visited that site along with George Howard and Graham Hancock and Chris Moore, who's one of the leading investigators, scientists working on the Younger Dryas boundary event or events. And so we visited the Clovis Age Topper Quarry site and got a personal tour. It's on private property of it's in corporate property. We got permission, went in there and got the tour of the site by Dr. Goodyear. Malcolm, I don't think was there. We did attend a scientific roundtable that weekend that Malcolm was at, Malcolm LeCompte. But no, I don't remember. I don't think he accompanied us out to the site. Anyways, Sampling was conducted at the Clovis Age Topper Quarry site near Allendale, South Carolina, where a complete stratigraphic profile was collected in June 2008 from the surface to 4 centimeters below a Clovis layer containing extensive debitage or waste material resulting from stone toll production. At TPR, that is the Topper site, based on optically stimulated luminescence or OSL dating and cultural stratigraphy, the YDB layer dating to 12.9 thousand years before present is accepted by both Firestone et al. And Suravel, one of the critics, as being represented by a few centimeter thick layer containing highly abundant Clovis artifacts and debitage. For approximately 20 centimeters above the Clovis artifacts, there are extremely few human artifacts, indicating that the quarry experienced a multi-century hiatus in human activity, perhaps as long as 600 to 1200 years, after which the site was reoccupied. So this graphic here really drives home the point at the Topper site. So notice here, you've got the number of artifacts on the y-axis. So we have a graph depicting distribution of total known Clovis artifacts. N equals 453 projectile points, preforms, blades, and cores compared to post-Clovis. Now look at here. So you've got up here, this is so 453. They're finding up to the Younger Dryas boundary. And then look what happens. Boom. So there's clearly considerable amount of cultural activity associated with this quarry site. And then right at the boundary, boom, you have a depopulation episode. Now, more and more evidence is accruing that shows the same kind of model at many sites, not just in America, but in Eurasia as well. And again, I keep referring to this, but this is all part of the detailed story that we're going to unpack, right? Now, in some of the older interpretations, the assumption was, oh, well, these guys got up and they left. They emigrated somewhere else. They moved on for whatever reason. Well, then you look at other sites where they supposedly moved on to, and you see the same phenomena. And instead of being indication of mobility of cultural groups moving to different sites, it's pointing much more directly at essentially a mass extinction event involving humans. Now, here's the thing. This is exactly the interval that represents the final catastrophic demise of the great megafauna, the great Ice Age megafauna.
Did they move too?
Well,
they took them with them. The Clovis people took the megafauna with them, Randall. Well, that's the only logical.
Well, yeah, you can see on some of the rock art, you're seeing the chieftains of the Clovis riding on the woolly mammoths while all the other extinct megafauna are falling behind. But no, I don't think that's what happened. Let's see. So, this is part of the same paper. This is a great paper. I wouldn't be a bit surprised if we could find this paper, if somebody was interested in going into it further. I wouldn't be surprised if this was actually available on Google Scholar. You might pull up Google Scholar and put it in if somebody wants to read this, and it is available. I'm not sure that it is, but we could check here relatively quickly. And
independent.
Yeah, independent.
Evaluation of conflicting microspherules.
That would be enough, microspherule. And what I'm seeing here is, by golly, it's available. So people listening, go to Google Scholar, type in independent evaluation of conflicting microspherules results, and you can download it in PDF form. That's awesome. So this is a graphic that appeared in the paper relative to Younger Dryas boundary. Now, Blackwater Draw is one of the places where we find the black mat. Brad Young, myself, Russ, and Kyle Allen, the Serpent Brothers. We were with a couple other guys. I don't remember who. We visited this site a few years ago, Blackwater Draw. I've got some great photographs. I mean, there's some very prominent black mat layers that are easily found when you go into the site. So this is a graph showing the stratigraphic distribution of magnetic spherules concentrations less than 53 microns grain size fraction. So right here you see there's a peak of these magnetic spherules right here relative to the Younger Dryas boundary. So the Younger Dryas boundary is 0, right? So look what's happened. There's a few that show up down here at, what is this, 24, maybe 30 centimeters down from the Younger Dryas boundary. Now this would be at Blackwater Draw. This is the Younger Dryas boundary is the black mat. So 0 would probably be right here would be, so you've got, looks like 2 pulses. But this is obviously the major one where you've got magnetic spherules. And then interestingly, at 48 centimeters above Younger Dryas boundary, there's another spike. It's not nearly as prominent. Could this be a secondary accretion event, impact event? Maybe. Maybe this could be some of this, the fleeting but tantalizing evidence for a later impact. I'd be interested to know how this might correlate with the upper Younger Dryas boundary. Here we're looking at 12.9. We actually know now it's between 12.8 and 12.9, but I just like 12.9. 12.9 here, right? I don't know that he doesn't give a chronological scale of this. It's simply the depth. But yeah, it looked like there is some accretion of magnetic spherules 48 centimeters above the Younger Dryas. But clearly right at the Younger Dryas, you've got, is where they found the concentration of magnetic spherules, which are consistent as proxies for an impact event. So yeah, here's the sampling site. The Blackwater Draw sampling site showing the YDB layer as a dotted line. Right here, that would be this line, this stratum. The YDB sample location at the orange bar right here. Other samples at yellow bars. Okay, so they took a sample down here, and they took a sample up here. Let's see. Stratum F up here has been excavated and is not visible in this photo. Okay, so they sampled a site that apparently had subsequently been excavated. Black arrows point to bones from a post-Clovis bison kill dating to many hundreds of years after 12,900. There we go, remains of a post-Clovis kill site. There are no artifacts known in the intervening strata. Between here, the kill site, and here, there are no artifacts found, which again supports the conclusion that the population disappeared. So the topper site, again, from debitage centimeters. Yeah, so here you've got, let's see, what do we got? Topper site graph showing the stratigraphic distribution of magnetic spherule concentrations less than 53 micron grain size fraction. Clovis debitage is at 0 centimeters right here. So look right here. Here's Clovis, and then look what happens. Right on top of where the Clovis debitage is, you've got this huge spike of magnetic spheral concentrations. And then again, you've got this other one, looks like a lesser event up here. I would love to have some dates on these.
And just for those who are joining us for this episode, Randall, just remind me again, why are spherules important? What are they a proxy of? And what can't they be anything other than?
Because they are produced in extreme environments of high temperature and pressure, 2,000, 3,000 degrees centigrade and more, up to 4,000. And there's no known, the only other known source for temperatures that high is in nuclear weapons testing, nuclear weapons explosions. So this is evidence of some kind of a very high energy event that involved temperatures of thousands of degrees centigrade. That's the importance of the spherules. Okay, topper sampling site showing the YDB layer as a dotted black line atop Clovis debitage. YDB sample location at the orange bar. Other samples at yellow bars. So yeah, you can get this paper yourself. Here we go. Here's the answer to your question. Magnetic spheral surface morphology is distinctive when created by processes involving high temperatures followed by rapid cooling, such as during meteoritic atmospheric ablation and impacts. A variety of spheral forms, 16 subtypes, were found to be relatively ubiquitous in small concentrations throughout the soil column. The spherules were categorized according to their distinctive polygonal and dendritic surface patterning or microstructures formed by rapid crystallization, indicating that they were in a molten state and rapidly quenched. These spherules exhibit the surface microstructures which are consistent with formation at high temperatures followed by rapid quenching. In summary, we found that scanning electron microscopy analysis to determine microstructure and the application of a correction factor are essential because true YDB spherules cannot be reliably identified by light microscopy alone, as was attempted by Suravel et al., Pinter et al., and Pagatti et al., all of whom were part of the clique of critics attempting to discredit the Younger Dryas impact. And they only used light-based microscopes. They didn't use SEM. They didn't use scanning electron microscopes. And that was one of the reasons, just one of a number of reasons, why they did not find the proxies that Firestone found. And then they made a big to-do about publishing the fact that they didn't find these proxies, and therefore the work of Firestone and others was not replicable, and therefore that was then used to discredit. But we can go through, it's a very interesting exercise to go through the claims they made and the debunking of their attempts, the debunking of the debunking, all right? So this just shows you some of the varieties of the YDB spherules, displaying some of the wide range of surface microstructures indicative of melting and rapid quenching. The top three are from above the debitage layer at topper, right? The middle six are from the Blackwater draw in the DC layer, and the bottom are from the Pawpaw Cove. I think that's Pawpaw Cove. Where was that? New Jersey, maybe? Maryland. The Pawpaw Cove site is an archaeological site on the coast of Talbot County, Maryland. The site, first identified in 1979, is a complex of 3 locations on 500 meters of shoreline on Chesapeake Bay, at which stone artifacts with an estimated date of 11,500 to 10,500 years before Common Era have been found. So you can look, this is some interesting, look at this one was hollow and it's busted, probably from colliding with another one. And here, what you have is a larger spherule that was bombarded by smaller spherules, but in the high temperature, high pressure environment, the smaller spherules, they embedded themselves. They fused themselves to the larger ones. And if you look at this one right here, interestingly, after it fused, it then collapsed. So this was apparently a hollow one, and then it collapsed. So they're almost like little warts, but these are smaller microspherules fusing to a larger microspherule.
Like we said a couple of times back, the spall, and someone corrected me in the comments section. You're right. I was tired. I said sprawl. It's spall. The spall from metalwork.
Yeah.
You know, as a child, I would go and I would look at the spall. I'd pick up each one of these and look at how they all melted together. Only under the heat, intense heat, do you ever get something like this. And
Correct.
it's only from impact. Heat and impact.
Yeah. Yep. So I think this is probably a good place right here to,
put a pin in and come back next time.
Oh, yeah. And I can assure people listening, if you follow this, if you put forth a little bit of the effort to follow this amazing scientific work and ponder the implications of this work for the bigger picture of where we came from and where we're going, I think you'll find it worthwhile. And so I want to encourage people, yes, to exercise your attention span and stay with us in this journey, because what John Arthur and I are going to attempt to do here is to lay out a great concentrated summary of the whole Younger Dryas phenomena from its inception up to where it is now. And we may take several episodes to cover all of the material, but stick with us, and hopefully what we're doing here is going to create a team of quasi-experts who can talk intelligibly about the Younger Dryas boundary. I still see people online saying, oh, that's been disproven long ago. I'll still see that. Although that kind of a comment is not nearly as prevalent as it was 4 or 5, 6 years ago, I'm still seeing people, and of course those are people who have not invested the time or effort to keep up with the pace of scientific discoveries. And but it is continuing apace, and what we're learning has tremendous implications for understanding the bigger picture of human life on Earth and our civilizations that we've attempted. So we've got a lot more interesting material coming up to cover. So I hope you stay with us, and we'll try to deliver the goods as best we can. So, John, I'll turn it over to you for some final words, perhaps.
Well, it's been a privilege sitting here listening to it. I'm looking forward to doing a little bit more digging on 1913. And at some point, I think we should do a closer look at some of the literature on all of the eyewitness testimony on that, because there has to be some good information on that.
If you do some digging, that would be awesome.
I will.
If you find anything, yeah.
And anyone in the comment section, I know you guys are listening. Randall, you and I can't get away with anything on this, and that's good. If someone in the comment section has a good source, feel free to drop it for the 1913 meteor stream. Want to look at that? What
did you just say? Somebody in the comment section?
In the comment section. Is that? Did you just dub the Randall Carlson comment section the comet section?
No, that's what I heard, but
I wonder if that's going to stick.
Oh, that's interesting. Maybe so. But, well, I consider it a positive. If somebody, like you said, you were tired. Sometimes I get really tired, and we're trying to do, and, I'll misstate something, or I'll mispronounce a word here and there. Let's see, what was somebody recently getting on my case for?
Supposedly.
Supposedly.
So it's supposable that they should say supposedly.
Okay. It was something that was more of a, I don't remember what it was. Somebody was caught me. Oh, well, it was in a clip. I was referring to, I was talking about gneiss, GNEISS, which is metamorphized granite. But that was the larger picture. But the small minute or 2 minute clip that went up, I'm probably discussing some layer of granite, but I referred to it as granite, and I referred to it as a metamorphic rock. And somebody came and said, granite's an igneous rock, it's not metamorphic. Well, I was talking about gneiss, which is metamorphosed granite, right? So if they had seen the whole context, I think that would have been clear. But, it was a little bit of a faux pas, because technically I should have not referred to granite in the context that I did. But it's small things like that. But that doesn't bother me.
But it's a good thing. It's a good thing. And so if someone has a good reference on 1913, or if I mispronounced something again, put it down there in the comments section. Feed the algorithm, folks. Make sure you like and subscribe. All that good stuff.
There you go. Because, listen, that's going to help us. One of our goals is to get this to the next level. This is why we've been working hard to expand the network, to make the connections with the people who are doing the cutting edge work. And this is actually happening. And this network, I think, of people, scholars, scientists, independent researchers, and free-minded thinkers, we are in the process of, I think we're altering the paradigm. And it's a paradigm that I think is going to be critically important going forward. It's not just an abstract academic pursuit that we're engaged in. And if we can help to raise some more money, that the Comet Research Group can do some of its critically important work, if it allows us to reach a wider audience, to do the field research like we've been doing. And it was very gratifying, John, that you were able to join us that week out in Utah and Idaho, and did that amazing job of documenting everything that we did and saw and where we went. And I know that's going to be edited. Coming up, it's going to be edited into a sort of a documentary style presentation. But we haven't had that level of professionalism in terms of documenting our tours and our reconnaissance out in the field, our field studies, like you were able to accomplish last on our Bonneville flood tour. But this is the kind of thing that support is going to help us do more and more of. And eventually, the idea, and Beckett and his team over at Titan Zero are working on the presentation of a model of an institute, a school, a center, a conference center that can serve as a hub where this kind of information, these kind of ideas can be brought together on the next level. And we can literally create, I think we're in the process of creating a global community of people who are now thinking outside the old standard models of history and prehistory. And it's going to be so exciting to see where this goes.
So drop a like, drop a comment, and we really appreciate it. And if you got any criticism, drop that too. We always look for constructive criticism.
Yeah, but if you have criticisms, now direct most of them to John.
I'll take it.
Okay. Just kidding, folks. All right. See you on the next episode of Squaring the Circle.
Bye, y'all.
Bye.